All right, it is 2, so we will get started here on our last Friday lecture of the semester. It's hard to believe that there are no more Fridays in the semester after this. So I did put up on the announcement, the rest of our schedule. So if you haven't seen that yet, please do. I'll tell you what's going on. Just a reminder, the Wednesday that's coming up, the Wednesday before Thanksgiving, we're not going to have a lecture during that. I don't think it's an official school holiday to have Wednesday off. I could be wrong about that, but yeah, I'm not going to be holding lecture there. It'll be a day for you to study or get ready for if you're doing something or if you're not doing something because of COVID. Still your early holiday treat from me to you. All right. So what we were talking about all this week really have been enzymes. So we just got into this PowerPoint. We didn't get too far into it, but we were talking about looking at the different type of mechanisms again and reminding ourselves, how does organic chemistry work? And then we looked at mechanisms. So we looked at acid and base mechanisms. And we looked at an acid and base mechanism in the ketol-enol tautomerization reaction. Then we looked at an acid and base mechanism for RNA ACE, where we're using histidines to hydrolyze our RNA here. And so for this lecture, I'll probably answer most of the questions just because we're a little bit behind and we're running out of time to catch up. So we talked about this on Wednesday, but on a chemical level, how are the acid and base mechanisms helping to speed up the reaction? And really, this is every enzyme. They will stabilize the transition state. So here's our transition state in our example ketol-enol mechanism, where we have a carbon, a CH2 molecule that's partially negative, which is really unfavorable to have. And so what the acid is doing is that it's removing that hydrogen, which will allow this CH2 to become negative a little more favorably. It's just overall stabilizing the charge of the molecule. The charge is being more delocalized, I should say. In our uncatalyzed version, right, we have the charge being in like 2 places, on the carbon and on the oxygen. By not taking off the hydrogen quite yet, we are delocalizing the charge. And by spreading out the charge, is another way to put it, you are making this transition state more favorable. And the base is basically doing the same thing here, but here we're pulling the hydrogen from the carbon. In the acid form, we're giving a hydrogen to the oxygen. In the base form, we're pulling a hydrogen from the carbon, but it's the same idea. Stabilize the transition state is the main point to get across. How exactly is that happening? We are stabilizing the charges. We are delocalizing it. We are spreading out the charge. And we're going to see this idea all throughout this section. Stabilize the transition state. Have amino acids there to interact with different charges of our transition state. And question 3 is kind of a review from Wednesday. But in our RNA ACE mechanism, and I did ask this question already on Wednesday, in our RNA ACE mechanism, so that's what we're talking about here, histidine is an acid and a base. Why is histidine good for that? So histidine has a pKa of 6, right? And if you remember, when pH equals pKa, you are 50% acid and 50% base, right? Or you're 50% protonated and 50% deprotonated. Well, in the cell, the pH is 7. So and I should say, the pKa's I had you learn, those are kind of like baselines. You can change the pKa of an amino acid based on what you put around it. So pKa is not like a set number set in stone forever. pKa can be changed if you put different chemical groups around what you're looking at. So it's very easy for histidine to lose or gain a proton under physiological conditions, that is, in the cell. So when you look at acid and base mechanisms, and we're going to look at a couple of other mechanisms that do this, you're often going to find a histidine because it's easy to protonate and it's easy to deprotonate. Compare this with like arginine, right? Arginine has like a pKa of 12.5. So it's very hard to add the proton back onto arginine and make it neutral. So when we look at acid-base mechanisms, arginine is not going to be the thing you want to be donating and accepting a proton. The pK is too far away from physiological conditions, while histidine is right where you want to be at. And why can't RNase cut DNA? So going back to the mechanism, like the first step of that mechanism is to take the interact with the 2' hydroxyl, right? So we have one histidine that takes the hydrogen away from this 2' hydroxyl to make it a negative oxygen. Well, DNA does not have a 2' hydroxyl. Remember, it's deoxyribose. So for DNA at the 2' position, we just have a hydrogen. And without that oxygen there, we can't do the necessary chemistry. So we need that OH group for this whole mechanism to work. So that's why RNase can be specific for RNA and leave DNA alone. For the mechanism to work, it needs to attack that 2' hydroxyl. So any questions about RNase mechanism? Any questions about histidine or anything we've talked about so far? All right, we will move on then. And here I will actually I'll take a minute for you to try and answer this because I think everybody should be capable of answering this on their own or near. I want you to draw a reaction coordinate diagram that shows catalyzed and uncatalyzed reaction. If you don't remember, energy was on the y-axis, reaction coordinates on the x-axis. So there was a question. So any amino acid close to 6 can be easily protonated and deprotonated. In water, yes. The cell is roughly at 7. So if your pK is at 6, you can easily lose or gain a proton. Depends on the medium. We're going to see today, hopefully, if you change the environment, then you can change other things. But yeah, if you shift amino acids up to a pK of around 6 and 7, they can easily lose or gain a proton. All right. But take a minute and see if you can figure out reaction coordinate diagrams. Remember, we looked at these already when we first talked about enzymes. It's our energy diagrams with reaction coordinates. So I'm going to give you a minute or two to think about that, and then I'll come back and give you the answer. All right, so the hardest part of this question, I think, is just remembering what are reaction coordinate diagrams. And if you're struggling to remember that, once I show you what they are, it should be like, oh, that's what those things are called. Okay, so we start with our reactants. They have some sort of energy. Then we have our transition state, that's very high energy. And then our products. And if the products are lower, delta G is negative. So what I wrote there was delta G is a negative reaction. And that's, I just drew an uncatalyzed version. The catalyzed version, let me do green here. The only thing it changes is the energy of the transition state. The energy of the reactants is the same. The energy of the products is the same. Delta G is the same. The only thing that changes is delta G double dagger, where that difference is called delta G double dagger. So that diagram is a reaction coordinate diagram. And just a little reminder, refresher here, the way enzymes work, and this is just, I'm gonna be saying this a million times because it's the essence of an enzyme. The way an enzyme works is it lowers the energy of the transition state. Any questions about that idea still? Well, so got a question. So the uncatalyzed is double dagger and the catalyzed is delta double dagger. Not quite. Let me just go over what those terms mean again. The energy from the reactants to the transition state, this gap is called delta G double dagger. And the double dagger is just saying, we're looking at a transition state energy, right? So it's, if I was going to say it in more plain English, it's what is the change in the free energy when you look at the reactants compared to the transition state? And the transition state is always higher in energy because it's usually some weird chemistry that doesn't like to happen. You have like negative carbons or stuff like that, just molecules that do not like to exist. So they're very high energy. So that's delta G double dagger. And when we catalyze a reaction, we lower that energy. So the green is also a delta G double dagger, and we can call it cat for like catalyzed, and I can call the red uncat for uncatalyzed. So technically, they're both delta G double daggers because they're measuring the same thing. And the difference between those two energies is what we call delta G double dagger. if I was going to try and say that in a sentence, it would be the change in the free energy when looking at the reactants compared to the transition state when you're comparing a catalyzed and an uncatalyzed reaction. It's quite the mouthful. That's why I think pictures work very well in getting that idea across. And the two deltas, again, means the change of free energy. Does that make a little more sense, what those variables mean? Yeah, it's all super confusing. The first time I saw delta delta G, I was like, what is going on? What does that? I don't even know what delta G means, and you're throwing in another delta at me. All right, now I know what delta G means, though. So you'll get it eventually. All right, so we just looked at an example of acid-base catalysts with RNase. Now we're going to look at an example of covalent catalysts. And the covalent catalysis is exactly what it sounds like. Here we are making a covalent bond to our substrate. So previously we were just doing acid and base chemistry. Now we're going to do covalent chemistry, or covalent bond formation and breaking. And the system we're going to look at for our example is decarboxylation of acetoacetate to acetone. This reaction happens, one of the things this happens in is when you are not fed, when you haven't ate. And that's one way to make like ketone bodies, is to do this reaction. This reaction can also happen when you have diabetes, because when you have diabetes and it's untreated, that's basically the same thing as starving yourself almost. And so your body will go through this process and you'll make acetone. Acetone is a nail polish remover, and it makes your breath super sweet smelling. So one of the ways to test for diabetes, if you don't know you have it, is your breath always smelling sweet? If so, you probably have diabetes. And so this reaction is a decarboxylation reaction. So on the top here, we have our uncatalyzed reaction. Super slow. It does happen by itself, but it is slow. We do have, we can do this chemistry using a catalyst though. And the way we're going to do it is through making a Schiff base. So Schiff base. So this molecule down here that's what we're calling our Schiff base. So let's look at our catalyzed reaction here. So we need an amine group to come in. And what's going to happen is that we're going to take our carbonyl oxygen here, and we're going to make it hydroxyl. So take one hydrogen from here, combine it with the oxygen from here, and you kick off your OH. And now you have made a covalent bond. So you can think of this red as an enzyme, right? Like this, that R group could be the rest of your enzyme, and the nitrogen is just the group that's doing chemistry. So maybe this is like an asparagine amino acid that's doing this chemistry, for an example. And once we have this molecule, well, now we can remove our CO2 more easily, because here we have a positively charged nitrogen, and we have that positively charged nitrogen forming a double bond. Well, the resonance structure for that is if you had the nitrogen just be a single bond, as shown here. And if that nitrogen becomes a single bond, that means our carbon needs to get another bond, which happens when the CO2 leaves. So the CO2 leaves, we form a double bond between the carbons, and we have a single bond between the carbon and the nitrogen. So we have done the reaction, but we're not quite done yet. We have two problems. Well, actually we have one problem that you can say in two different ways, but the problem is substrate the substrate is still attached to our enzyme. So we want to release the substrate, and we also want to restore our enzyme. So that's what's left to be done. We need to let the substrate go back into the cell, and we need to restore the substrate, or sorry, the enzyme back to its original form. So the first thing we need to do is bring back down the electrons that we had to form our single bond. And to do that, we need another hydrogen. Because if we didn't bring down another hydrogen, this group here would be CH2 with a lone pair of electrons. Carbon does not like a lone pair of electrons. So we have a hydrogen come in to make it CH3. Then we can just use a base and remove our amine group, and we are at acetone. So here, it kind of looks like an acid and base reaction, right? We have acid and we have a base. But this is actually covalent catalysis because to get to the transition state, right? Here's our transition states. We really need to covalently attach to our substrate, which allows us to kick off the CO2. All right, so that's a lot of information on one little slide, but any questions about any of the steps I went over, any of the logic, what's going on there? Right. If not, we can continue. One thing I did want to mention, and I'm going to erase my drawings at this point, is that a lot of times in these mechanisms, we're going to see like the first and last step are a lot of times the same thing, but in reversed. Or in general, what mechanisms do is that they'll do one thing and do the other and do that same process again reverse. So what I mean by that is that in our first step to attach to our substrate, we kick off a base, we kick off hydroxide. Well, in a last step to be removed from our substrate, base comes in, hydroxide comes in. And we're going to see that a lot when you look at mechanisms, that many steps repeat. They just repeat in the reverse order. So that is something to be on the lookout for as we talk about mechanisms. So here's a question, and I'll see if anyone can answer this, I suppose. Why, when we form a covalent bond between the enzyme and substrate, does it need to be transient? Or remember, if you don't quite know what that word means, why does it need to be temporary again? Now, I did mention it. So why is that? Anyone? Why in this mechanism is that covalent bond not permanent between the substrate and the enzyme? Nobody knows? Yeah, the enzyme needs to come off, exactly. I guess another way I could ask that question, why doesn't the substrate permanently attach to our enzyme? Well, imagine, let's say that scenario happened, right? Let me ask that question in a different way. Why would it be bad not dead. Why would it be bad if the substrate was always bound to the enzyme, or the covalent bond never broke? And if that happened, we wouldn't be able to reuse an enzyme, right? One of the benefits of an enzyme or any catalyst is that it can be used for multiple reactions, right? And so let's say we just went here and then we said, stop, you're done. That doesn't happen. Well, your enzyme's now dead and you never release your substrate. So your substrate can't be used for anything else. All you did was knock off a CO2. Your enzyme can't be used for anything else, right? You have just spent a lot of ATP, a lot of resources into a molecule that basically did one thing and then died. So enzymes, one of the things for an enzyme is it needs to be reusable. And so every time we look at a mechanism, the last few steps of that mechanism is restoring that enzyme. So make sure you understand that point. Enzymes have to be reusable. So anything we do to our enzyme in the course of our chemistry, in the course of our mechanism, we have to undo. Otherwise, the enzyme would no longer work. Questions about that idea? All right. So we looked at covalent catalysts, we looked at acid and base catalysts. Now we're going to look at metalloenzymes. And metalloenzymes, 1/3 of all your enzymes in your body use metals, and they're doing their chemistry. So it's very important that every day you eat some metals. So just go outside, find some metals, and nom them down. And the way that metals work is that they have three major purposes. One, they can bind to the substrate and reorient them properly for any reaction that they're doing. Two, they're really good at redox reactions. And so usually, the metals used in this chemistry, a lot of the times will be transition metals. Not always. Magnesium is used a lot, but a lot of the times it can be like irons or zincs, right? And copper is also a very popular one to be found in your enzymes. And these can have different charge states. And so they can work with redox reactions because they can adopt these different charge states, or by stabilizing negative charges. So for example, anything that works on DNA, it's like almost 100% guarantee that that enzyme is going to have magnesium in it, because DNA is incredibly negatively charged. And so to interact with that negative charge, enzymes usually have magnesium so they can bind them, right? And one thing also metals can do is that they can make things more acidic, and specifically water. And this is done with the enzyme carbonic anhydrase. And does anyone remember where we talked about carbonic anhydrase? About, 6 months ago, not 6 months ago, 6 weeks ago, I want to say we talked about carbonic anhydrase. Blood buffer. Yeah, exactly. So when we were talking about hemoglobin, right? We were talking about how, when the muscle cells are going through energy, or any cell really, one of the byproducts is CO2. CO2 is not soluble in the blood. And so to make it soluble, you have to make it into HCO3 minus, which also are H2CO3, which makes it a good buffer. So carbonic anhydrase works as supplying your blood buffer, and also works by moving CO2 around. And when we looked at that reaction, I just said, it happened, and we didn't talk about why it happened, and we just moved on with our day. Well, the way it happens is that in this enzyme, we have a zinc ion. And that's what's being shown in our bottom picture right here. We have zinc. And what zinc can do is that it can make water more acidic. And that's kind of what's being shown here, where we have a zinc interacting with an OH molecule. So by interacting with H2O, it has already caused that H2O to lose a proton. And when it loses that proton, the oxygen is now negative and can interact with that zinc. Well, OH minus here with 2 lone pair electrons is a perfect a nucleophile, in that it will go and attack that CO2. It will attack the carbon. And when it attacks that carbon, then you have the double bond from oxygen moving to form a single bond. And you can now break this zinc oxygen bond by bringing in another water. And now you have HCO3. So for our blood buffer and to move CO2 around the body, we use carbonic anhydrase, which is a metalloenzyme with the main ion being zinc, and the main mechanism being it's helping to attack that CO2 with water. So any questions about our metalloenzymes or anything on this slide? All right. So just talking about enzyme theory in general, we've been looking at mechanisms pretty in depth. Let's take a step back and look at the broad picture. How do enzymes actually favor the transition state? How do they lower the energy of the transition state? And they do this in 4 ways. 1, they actually bring substrates into contact with each other and pointing in the right direction to make the transition state. So bringing them together is called a proximity effect. Making sure they point in the right direction is an orientation effect. Taken together, this speeds up a reaction roughly 500-fold. That sounds like a lot, but that's actually still slow. Like just speeding up a reaction by 500 times is probably not enough to keep you alive. Reaction needs to go much faster than 500 times its normal speed. So they can bring it together, they can orient it in the right way. They can also help with charge groups stabilizing the transition state. So that helps, like we've been talking about. But the main thing that happens is they stop the translational and rotational motions of the substrates and the catalytic groups. So we know from organic chemistry that single bonds can rotate, single bonds can fluctuate, and the molecules themselves move around all the time. Really, why an enzyme works so well is that they take the substrate and they like hold it in place and say, okay, you stop moving so we can do chemistry on you. And then it'll kind of like more or less freeze it in place and put it in the exact perfect position to do its chemistry. And so taken with all that in effect, putting the substrates together, orienting them in the right way, balancing out charges and stopping it from moving or rotating, you're looking at speeds up of roughly 10 million, 100 million, a billion, a trillion times, right? And it's at those speeds that we really need for life to happen. Now, doing these actions, taking your molecule and kind of freezing it in place, that is a very ordered molecule. And remember, the universe hates order. the universe loves chaos. So there is an entropic penalty to this and to becoming ordered. And so to get over this entropic penalty, this negative delta S, we have free energy of binding. That is, when we bind our substrate, we make new interactions, new bonds that help to overcome this entropy penalty. New bonds. And this could be like hydrogen bonds, ionic bonds, covalent bonds that we talked about with covalent catalysts. But anyway, we bind our substrate, it's helping to overcome the penalty we have to take in order to hold it still. And I talked about this to death already, so I'll go over it really fast. The way that enzymes work is by bonding the transition state. And I think the example in the book has a beautiful way of talking about why this is. And so let's just focus on this picture, right? So in our mechanism, we want to break a metal bar, right? That's what we're trying to speed up. And let's say that our enzyme, in example B here, or picture B, our enzyme wants to bind the substrate. And so how do you bind a metal bar? Well, you bind it with magnets. So our enzyme binds our substrate perfectly. But we want to break the bar. So how are we going to break it now that it's fit into this nice little pocket? If anything, we made the bar harder to break. And that's what's being shown here in this energy diagram, right? We start with the energy of our substrate, and it actually becomes more favorable to form this complex. Once the enzyme binds, that's super favorable. So it becomes harder to get to our transition state. So this actually slows down the reaction. This is the opposite of a catalyst, right? This is making our reaction slow down. While here in picture C, we bind our substrate okay, not perfectly, but what we are binding perfectly is the transition state. Our active site is perfectly shaped to bind our transition state, which lowers their energy of our transition state, breaking our molecule. So this just shows that, like I said 100 times now, we make this faster by really binding our transition state. And humans have figured this out because we're pretty smart. And we've also figured out if our enzymes want to bind the transition state so bad, the way to make an enzyme not work is to give it something that looks like a transition state, right? So here in this example, we have an enzyme that just goes from L to D proline. We just switch our chirality. And our transition state is a perfect plane here of our proline. If we don't want that enzyme to work, what you do is you get a molecule that looks a lot like your transition state, but it's a little different. So we have a couple extra bonds here. And because we have these bonds, we can't continue with the chemistry. So what will happen is that your enzyme will bind these, but then it's dead. It will not unbind the transition state because that's what it really wants to bind. And it's a dead enzyme once it binds these. These are called transition state analogs, and they are really good antibiotics. If you want to kill bacteria, you know what enzyme you want to kill. Give it something that looks like the transition state, then you have a dead bacteria. Drug design, when we want to design a new drug, this is basically what you do. Is if you know what the protein that you're targeting looks like, you know what the active site looks like, you can use a computer to make, a million, not really a million, more like 20,000 different drugs that look like the transition state. You do computer calculations to see which one binds the best. Then you take like the top 500 and then you hire some organic chemist to make these for you. That's what organic chemists are used for. They're making drugs for the biochemists. So you say, hey, organic chemist, make me some drugs based on my computer calculations. They say, okay. Then you come back and you do a real experiment to see how well these bind your enzymes. That's the basics of drug design 101. What do you mean looks like a transition state? Don't you want the enzyme to bind the transition state? Yes. What I'm saying here is, what if I want to inhibit the enzyme? What if I want the enzyme not to work anymore? So I'm going to create a drug that looks like the transition state of its real chemistry, right? So that's why the example here of, this random enzyme, the normal reaction will make L-proline to D-proline, right? And this is the transition state of that reaction. Well, if I don't want that enzyme to work for some reason, what if I made a drug that looks just like the transition state? What will happen is that the enzyme will bind that drug and it will stop working. So this is for inhibition. And usually when you're trying to kill bacteria, you want to stop a specific protein. So that's how antibiotics work. All antibiotics are is they usually just go and they bind a prokaryotic protein to kill that bacteria. Does that make more sense what I'm talking about? Yeah, it's 100% a transition state decoy. That's 100% what it is. Once they bind it, yeah, they're not going to unbind it. You have a dead enzyme. Yep. That's how drug design works. Right. Any other questions? So those of you who are thinking about pharmacy, farm school, you're going to be talking about this a ton, I'm sure, this whole concept. All right, we will move on then. Or medical doctors too. I'm sure you're going to talk a ton about this concept. All right, so how do metal ions participate in catalysis? Again, this is a review question. So we already covered it in this lecture. The answers are on like 3 slides ago. So I'm going to leave that as a review question for when you're reviewing the test. The answers are in the previous slides. And same as question 7, just to save us some time. I'm not going to repeat what I just talked about for the last 5 minutes. So use these as a good way to study for test 4 on December 2nd. When you're going back, look at your notes, make sure you can answer these questions because you might see questions like these on the test. All right. So we do have a little bit of time. So let me get into our next lecture here. And I know we are a little bit behind, but like the last lecture of this course only takes like 15 minutes. So we should have time to finish everything.